Now finally let us have a few words about power BJTs. Now as I said, in a power amplifier application, you need to use special BJTs, especially if you are talking about applications with kind of, let us say, greater than a few watts, then you need to use BJTs which are special BJTs. Now a typical example I gave was 2N3055. So when we talk about power BJTs, we can think of a few examples. Now this 2N3055, as I said, has a power dissipation of 125 watts, which is very high. Now this is an NPN transistor, and we know that you need a PNP also. If you want a class AB amplifier, then you need both PNP and NPN. So normally in the market you would get something called ECP and ECN, which are both made in our country, I think by ECIL, and both are actually matched. So they can think of both of them as in the same family with the same kind of power dissipation, and you need to use a pair of them. So they are meant for typically fairly high. Now occasionally you have applications which may not require that high. Now the problem with these BJTs, so far we were used to seeing BJTs with 3 terminals. Now if you look at a 2N3055, the device would look something like this. Now you would find only 2 terminals. One of them is the base terminal, one of them is the emitter terminal. Now one would wonder, where is the collector terminal? Now the body itself is the collector terminal. Now you might remember from our discussion of BJTs in our first lecture on BJTs, you will remember that in a BJT the collector region has the largest area. Now this is done, at that time we said this is done from the point of view of power dissipation. So in all metallic, even small transistors, even metallic transistors, it is a common practice to tie the collector to the metallic case. So the collector is generally tied to the metallic case. Now in the example of this particular transistor 2N3055, how do I make a connection to the collector now? Because I don't have a terminal. How do I solder, or how do I physically connect? Now therefore maybe those of you who have already used this particular device might know. Now if you go to the market, what they provide is, these devices are generally mounted on heat sinks. Now as I said, one of the problems in a power amplifier as compared to the small signal amplifiers we talked about so far is, in all power amplifiers, irrespective of whatever is the efficiency, you would have the problem of power dissipation, and that is a problem we have to live with. So you need to think about ways by which you are able to dissipate the power efficiently. Now the way it is done is, in a transistor like this 2N3055, the way it is done is, the metallic case is made large, the area of the outside area is made large, and on the top of that you are expected to mount this particular device on a heat sink, on an aluminum heat sink. So now I would encourage all of you in your own remote centers, if you have a kind of a public address system available, maybe during tea break you could have a look at the power amplifier, because power amplifiers are very easy to locate. The simplest thing is your standard public address system which is used. Now if you look at the rear of that particular the public address system, you would see one of these transistors. Most of the time 2 and 3 sort of 5 is used, and then you would see how it is connected. So the way it's done is, you would have because if you directly touch the body, which is the collector, to the heatsink, you cannot put a second device. You have to then insulate this particular one from the body of the instrument. So what is actually done is, you would use a electrical insulator, but at the same time something which would conduct heat. So what is actually done is, you would use a kind of a mica kind of a sheet. So these are things which is very nice to maybe show to students when you teach this particular topic, and those students who may be doing it, they may be seeing. So it's very nice to see. So the way you would connect is, you need to have some kind of a screw arrangement by which you would tie the collectors. So you would connect a kind of a nut and a bolt, and normally it's kind of a good kind of a brass screw, and then you would put the mica sheet on the top of the one before you actually mount it to the heatsink. Now with this arrangement, the purpose of this is, whatever heat generated in the device is easily kind of dissipated in the heatsink. Now if this is not done, as we saw right in the beginning, the device can get damaged. Now there is something which is extremely important to remember. Now we need to differentiate between the junction temperature and the outside temperature. Now we need to think about the junction temperature as compared to the outside temperature. Now as far as the device is concerned, what is important is the junction temperature. So the junction temperature should be kept, let us say, much less than 150 degrees centigrade. 100 degrees centigrade is the boiling point of water, and we all know how hot it is. So, and generally if you don't have a good heat dissipation, your hand will literally burn if you touch one of these devices. So you need to ensure that the junction temperature is much smaller, but unfortunately right from the junction to the outside, now how efficiently it is connected depends on, so the outside temperature in an actual device, the outside temperature of the device, if the junction temperature is T1 and the outside temperature is T2, then you would see that ideally T1 should be equal to T2 so that it dissipated easily, but actually you would see that T1 would be greater than T2. So that shows how efficiently or it is done. Now this is done in the case of a power transistor. Normally this is expressed by an equation which is called Tj minus Ta is equal to theta Ja times Pd. This is an equation which is used to express this particular problem we are talking about. Now what this says is, the junction temperature minus the ambient temperature is what is called a thermal resistance. This theta Ja is called the thermal resistance times the power dissipation. Now how good or bad the heat sink or your heat dissipation scheme we are using depends on how small this value of thermal resistance is. Now the lower this value of theta J is, the better the heat dissipation is. Now the most common way of dissipating heat is through heat sinks. However, the problem with the heat sink is it takes too much space. Now in very sophisticated instruments there is another way of dissipating heat, or rather keeping the device cooler. One very important thing to remember in the case of a heat sink is that even in the ideal case, the temperature you can achieve is only the ambient temperature. So if you are talking about a room temperature of 30 degrees, you are talking about at best the junction temperature being 30 degrees. let us say that you have an application where you want to keep the device at much lower temperature than the ambient temperature. In such cases, you would use what are called thermoelectric coolers to ensure that the device is kept cool. Now, what is important to notice here is this topic of power dissipation in the context of a power BJT is extremely important. Again, there is a sketch which is drawn to express the importance of dissipating heat. Now, what I am drawing here is what is called the equation which shows the relationship now for every device, I'm sorry, I will draw it in again. So for every BJT, power BJT, the manufacturer would give you a characteristics like this, which shows the relationship between the power dissipation so what we have, this is essentially showing the maximum power dissipation, and TA0 Tj max, I will just come to this in a minute. Now, what this is telling is so you have so what this particular one is telling is, assuming that a device like a 2N3055, this 125 watts which we talked about is a case provided you are operating it at the ambient temperature. As you keep increasing the ambient temperature, the extreme is the maximum junction temperature. So, let us say the maximum junction temperature, let us say is 120 degrees or so. Now, at that particular temperature, the device cannot dissipate any power. So, this is the best situation. So, if you can keep the device at the ambient temperature, say 25 degrees, you will get the maximum power dissipation. Now, as your device gets hotter and hotter, the power dissipation comes down drastically. So, this is a very, very important consideration. So, this is why heat sinks are very important. Now, we could go on. So, at this particular stage, let's just have a quick recap on what we discussed today. So, what we discussed today was, we talked about power amplifiers, and we saw in some detail about their classification. One of the first things we said is, when we talk about power amplifiers, we generally don't talk about the kind of amplifiers which we are used to, the common emitter, common base and common collector amplifiers. Now, in those kind of amplifiers, we were only concerned about the signal, gain, input resistance, output resistance and so on. But when we talk about power amplifiers, we said we have some other very important considerations. Now, these considerations are, we need to ensure in these amplifiers that the output resistance are extremely small. When we say small, we are talking about, say, maybe an ohm or even much less, depends on the current. Another very, very important here is how linear our power amplifier is. And as I said, we never worried about total harmonic distortion in a common emitter amplifier, because if we could ensure that the input signal is within, say, a few millivolts or 10 millivolt or even 20 millivolt, we would get reasonably good linear output, we will get a good output. But in the case of a power amplifier, because we are talking about large signals, we will always have distortion. Now the issue is how small can I make my distortion. The third consideration, which again was never a consideration for us, is the efficiency. This was never a consideration for us so far in all our discussions, but in the discussion of power amplifiers, as we saw in the case of class A, class B, we saw that efficiency is an extremely important parameter here. This is because of the reason that from two points of view, the major interest is that whatever power you are not delivering to the load, that much power you have to dissipate on the device. Now just now I drew the thermal characteristics of a typical transistor, and we saw that the more the power dissipation, more is the temperature, more is the device would get hotter and hotter, and the more the device get hot, you need to dissipate this power. Therefore, one of the best option to take care of this problem is to use a scheme which is highly efficient, so that this problem is taken care of. And also, if there are applications where, especially kind of mobile or portable applications, you need to ensure that battery drain is reduced. Now we said that very special transistors are used in this power amplifiers. They are power transistors, and they have power dissipation capabilities from a few watts to hundreds of watts. And we talked about the classification of power amplifiers, and we said this is classified on the basis of the operating current, the DC operating current, and the signal current. In the case of a class A amplifier, we said that the DC operating current IC is chosen such that it is greater than the peak of the input sinusoid. Now by doing this, we are ensuring that at all instants the device is on, it is conducting. So therefore we are guaranteed to have extremely low distortion here. So this is called class A amplifier. Now coming to class B, this is a situation where we use two devices, and one device conducts for one half cycle, and the second device, a kind of complementary device, works for the other half cycle. So in the case of a class B, the conduction is only for a half cycle, as opposed to a class A where the conduction is the entire 360 degrees. So two devices are required here in the case of class B. Now class C, we said, is a very, very special case, and this is used only for very high power application, such as a transmitting station or so, where the powers we are talking about are extremely high. By the way, class C obviously would be much more efficient than, class C would be much more efficient than class B, and the kind of typical efficiency you can get in a class C application, class C amplifier, is in the order of 87 or almost close to 90%. Now these are used in very special, so we will not worry about this. Now what is of interest to us is class B. Now there is another class called a class AB, and this we saw later why it was required. So we said class A. Now class A amplifier, we considered the transfer characteristic, and we saw that it's a linear characteristic, and we said that this is very good. The minus point here was when we did the power conversion efficiency calculations, we saw that the maximum efficiency you could get is only 25%. Actually, in most of the times you will not even get 25%, you might get only somewhere between 10 to 20%. So therefore we said this is a very bad choice from the point of view of an output transistor. Then we considered a class B output stage, where we said you need two devices, one device for one half cycle. So the positive half cycle is taken care of by the top device, negative half cycle by the bottom device. But here we said, unfortunately, because there is no biasing, when the input signal is 0, no current flows, and you need a minimum of say around 0.5 volts for this particular device to turn on. So till that point no current flows, because of which we said we get what is called a dead zone. So in the transfer characteristic we get a dead zone, so which means say roughly between say +5 -5 plus, so +0.5 -0.5. So that's the period we see that there is a dead zone which result in what is called crossover distortion. Now we saw that from the point of view of power conversion efficiency, class B is very good. We can get as high as 78%, and we also said the power dissipation in a class B depends on the input signal, as opposed in the case of class A we saw that the dissipation is maximum when there is no signal, whereas in the case of a class B, when there is no input signal, there is no power dissipation, device is not on. But once you apply signal, the power dissipation keeps increasing and it reaches a peak for the case of 2 VCC by pi, and at that particular point you have an efficiency of 50%, and for the value of a peak input signal of VCC with a peak of VCC, you get an efficiency of 78.5%. So we said class B is very good from the point of efficiency, but it has crossover distortion because of the dead zone around 0 volts, and therefore is bad. And in this context we studied class AB amplifier, where we said what was done was a very small bias was applied. This is to make sure, take care of the dead zone, and we said this biasing has to be done extremely carefully, otherwise we would go from the, we want a situation as close as possible to class B, and therefore we would choose a bias very carefully so that it's just at the verge of conduction, so that we get efficiency at the same time without getting much distortion. And we said if you can ensure that, then you would get a linear characteristics and therefore ideally no distortion. And we talked about a scheme which is very commonly used in ICs, where you would choose a current based on the voltage you require here, and by changing the current you could choose any value of voltage here. And this has another big plus point. One of the minus points in a power amplifier is the heat generated, and we know that VB voltage is highly sensitive to temperature. Now here, because the biasing scheme is also using semiconductor device, they would all change together. So if they have a negative temperature coefficient, they also have a negative temperature coefficient, they will change together, therefore we will not have thermal runaway. So this kind of a scheme is generally used to ensure that you don't get a thermal runaway even when there is heat. So then finally we talked about power BJTs. We took the example of a few power transistors, and we talked about the importance of heat sink. So this brings us to the end of this particular talk here, lecture. I hope you followed the lecture here. The only thing to remember in this particular case is the considerations for a power amplifier are entirely different from the considerations we had for all the other amplifiers we studied so far. So thank you.